Good evening once again, and welcome to the last part on our series of average atomic mass. In this part, we will go ahead and calculate the mass defect and nuclear binding energy, which is the amount of the mass of the particles in an atom that gets converted to energy in order to hold it together. So, let's skip all the things that we covered before and go straight to the calculations. So as was mentioned in the previous video, in order to hold the nucleus together and overcome the repulsion between the like charges, the strong nuclear force takes into effect. And since it is a nuclear force, it involves the conversion of some mass into energy. This is why the total mass of the isotope, or the atom, is always less than if you just weighed up the sum of all the parts that went into it. The difference between these two things is referred to as the mass defect. And it's going to be one of the things that we calculate first in order to end up with a unit of energy for how tightly the nucleus is being held together. So the first step on the way of finding how much mass is converted into energy is finding out how much the mass of all the individual parts that make up an atom weighs. And that's going to be called the combined mass. And I'm going to provide for you the mass of a proton, a neutron, and an electron. Your job is to figure out how many of each of those you have in an isotope so you can compare the weight of all the parts to the weight of the actual atom, which will also be provided for you. So let's go ahead and calculate that combined mass. In this isotope of helium, we have 2 protons, 2 neutrons, and since it's neutral, we also have 2 electrons. And now I'm just going to multiply these numbers by the weight of their respective parts. And all of these masses are in atomic mass units. At this point, we have the weight of the protons, the neutrons, and the electrons. We're simply going to add up all of these to get the combined mass. And we can see that that is indeed slightly less, or slightly more, than the weight of the actual atom. This is slightly less than the weight of all the parts. So now we will subtract these two and find the mass defect. So this is the amount of mass that has been converted to energy, and we will refer to that as the mass defect. Now in the next slide we're going to go ahead and calculate this into energy. The relationship between mass and energy is the ever famous Einstein's equation from his general relativity. Energy equals mass times the speed of light squared. You've probably heard it all your life, but now is an actual opportunity to get to use it. One caution though, the mass must be in kilograms to use this equation. So heretofore it's been in an atomic mass unit. So we're going to need to do a conversion first before we can use E equals mc squared. Now that I have that in kilograms, I can plug that in as my mass in E equals mc squared, and of course the speed of light is 3.00 times 10 to the 8th. Don't forget to square that quantity. Now that we're in energy, our unit is joules. Now larger atoms, simply because they are larger atoms, are going to have more nuclear binding energy holding them together. So to make an apples-to-apples comparison between atoms of different sizes, we need to divide out by their size, their number of nucleons. You remember that from the first part of this series. It's simply the number of protons and neutrons, i.e. the mass number. So we're going to divide by the mass number so we can make a direct comparison. And there's the nuclear binding energy that I calculated from the previous slide. The mass number of this isotope of helium was 4. And so this is my final answer right here, which will be referred to as the nuclear binding energy per nucleon. Here's a graph of them showing how the nuclear binding energy changes across this. If you remember from your freshman class in the stellar evolution, the element that a star couldn't do anything with, the nuclear turnip in the life of a star, was iron. And that's because iron has such a high nuclear binding energy that it costs more energy for the star to try and fuse it into something else than it's going to produce. So if a star gets to right there, that's the end of its life, and it's going to probably turn into a massive black hole, or at least a pretty cool supernova. I want to do one more example here from start to finish so you can see it, and then wrap up this segment. For this example, I'm going to use beryllium-9. So the first thing I need to do is find my number of protons, neutrons, and electrons, and multiply by their respective particle weights. And then sum this. One of the things that I would have provided for you about this isotope is its mass. And its mass is... So now we can take the mass of the subatomic particles and subtract the actual mass to get our mass defect. So this is mass defect. Now to convert to nuclear binding energy, we need to first convert our mass defect from AMUs to kilograms. Now that can go in to E equals mc squared. to get my nuclear bonding energy. And that is now in joules. That is my nuclear bonding energy. And my last step in this process is expressing that on a per nucleon basis. The mass number of beryllium was 9. And so that is my nuclear bonding energy per nucleon. And that is it. There you go, guys. Another slightly lengthy calculation here, but always perform the same way. And remember that I'll be providing you with these masses, and I will also be providing you with the conversion from AMU to kilograms. So that's the process that you have to use with those numbers. Thanks again.